Monte Carlo tree search programs, and we limited us to normal CPU, where the Monte Carlo tree search runs, and one GPU, and it's a Tesla K20. It's still using Kepler, so it's quite dated and not the fastest available on the market, but it's built into our cluster where some older GPUs are built in. For training, we use the Caffe framework, which is a quite popular framework. It's very flexible, easy to use, and of course for free available. And in Monte Carlo tree search, we switched to the QDNN library of NVIDIA. The QDNN library is built in all major, is used in all major frameworks. It's also used in Caffe, so we can compile using this library, but it's a little bit more low level, so you have more control on what's going on. So for example, you can decide that you want to use asynchronous memory transfers to the GPU, and you can control synchronization, so one to get events back from the GPU. It also supports multi-threading, so we have a 16-core CPU, so we are running a multi-threaded Monte Carlo tree search. So it's essential that the library supports multi-threading, and it also supports multiple streams. So this is something from NVIDIA. So every thread in our implementation gets its own stream on the GPU. So when you, here we are. So when some computation starts and another thread runs in a different stream, then these executions can be run in parallel. So while we only send one board, so a batch size of one to the GPU, we don't fully can make use of all its parallel capacity. But if you have multiple streams and multiple threads pushing work to the GPU, then the GPU can be better utilized. And what's most important is it is compatible to Caffe. So if you train the models using Caffe, you have a very nice and easy way to train models, and then you can later just use these models and the learned weights directly in the QDNN library. In this paper, we use neural networks in the tree search phase, so one selecting moves. So if you later watch the lecture by Ajar, it's policy networks which we are concentrating on, not the value networks. So how do we use it? This is a selection formula of Abacus which we use. The first two parts with RAVE and the normal UCT are quite common. And in the last part, the model is used, so PSA means the probability of selecting action A in state S. So this is just where the neural networks plug in, and it says, for example, this move has a probability of, let's say, 0.5 to be good. And this knowledge is decreased by the number of visits of this move. So this is quite common formula which you find in many other programs. Sometimes you see a linear decrease in the visits, but it turns out that if you decrease it a little bit slower by the square root, it's much better, at least in the. So the main problem is that deep neural networks require a lot of computation time. Even if you run it on a GPU, it's quite slow. So our baseline uses basic patterns like shapes, and we have some common fake graph patterns and so on. It has a execution time of just the model is 0.38 milliseconds. And then we can just run the usual Monte Carlo tree search at a speed of about 11,000 pairs per second. And it has an accuracy on selecting the best expert move on some validation sets of 42%. If we now use neural networks, we can increase this accuracy a lot, so up to 55, close to 56%. But the execution times of the neural networks increase dramatically up to 10 milliseconds, which would, as if you use it as the same way as in the baseline, we would decrease the number of simulations we can do per second down to 2,300, which would, of course, hurt the playing performance of our program. So the simple recipe is add more GPUs. So this paper tries to use some other recipes in using only one GPU, but applying so-called replacement schemes, which I now try to explain. So first, some overview. So we cannot use the neural network in all tree search nodes. So we try to decide which nodes are important and which are not. So in the not so important nodes, we use a fast predictor, so the one we basically from shape patterns, and only those nodes which are more important, we use neural networks. And then the big question is, so what nodes are important? So we present 4 schemes on how to decide which nodes are important and later compare them. So the first 2 ones are basically done by, okay, Monte Carlo tree search, we visit more important nodes in the tree more often. So we just let Monte Carlo tree search decide by itself which nodes are important. So the first just increases the expansion threshold so that the search tree gets smaller, and then every node in the tree search gets the knowledge. The second one, the visit threshold, says, okay, we look at how often nodes are visited, and the more often a node is visited, the more important is it. And then we try to be clever and try to predict in before which node might be important. So we try a death scheme, so nodes near the root might be important, or trying to guess which will be the principal variation. I come to that back later. An important point is synchronous or asynchronous execution more important? Which means, should we wait for the GPU? Or should we just continue the search and replace the knowledge later? So this is a trade-off between good quality. So if you wait for the GPU, we can use the knowledge straight away. We don't waste any resources on maybe the wrong branches in the tree. But we have bad performance maybe. Or we just say, okay, we don't wait on the GPU, we just send a packet there and continue the search. So we might use not so good quality in the model for some time, but only later use the knowledge, replace the knowledge, and so the Monte Carlo tree search is not disturbed. So then we might have bad quality but better performance. So all the schemes are later tested in the synchronous and asynchronous way to show which mode of execution might be better. So now all the 4 schemes. So the first one is very basic. In Monte Carlo tree search, if you come to a leaf node, usually we say, okay, if there's more than 1 visit, we expand the search tree. So we can play around with this constant E and say, okay, we only expand the node if there are more than 8 visits to a move, and only then expand. So the default value for Abacus, for example, is 8. And if you know how to introduce neural networks, we can just increase it to, for example, 16, 32, which decreases the search tree, and so the number of nodes we have to initialize with neural networks decreases. The advantage of the scheme is that I try to shade it all the nodes where knowledge is applied by the scheme. So in this scheme, all nodes in the search tree at some point get the knowledge of the neural network. The disadvantage is that the search tree in itself gets much slower. So there might just be a trade-off between the depth, how deep we can search during some given time, or the quality. And by using the constant E, we can decide how large the search tree gets and how good our GPU has to be. The next scheme is named replace by visit threshold. So not every node in the search tree now gets the knowledge, which you can see, for example, here. And if a node has more than, let's say, 20 visits, so if this move was played more than 20, then this node gets DCNN knowledge. Other nodes just get the fast predictor. So we initialize every node by the fast predictor, and once we see, okay, the node was visited more than X times or T times, then we replace this basic model by the neural network model. The advantage is that this closely mimics how Monte Carlo tree search searches the tree. So we can build the same tree as before. We just say, okay, only the important nodes which are visited quite often by Monte Carlo tree search get good knowledge. The disadvantage is, of course, that not all nodes have good knowledge. The second one, now we try to become clever and say, okay, we don't let Monte Carlo tree search decide which nodes are good. We decide by ourselves that in this scheme, for example, we say, okay, nodes at the root level are extremely important because there we have to make decisions. And maybe nodes quite close to this level are also important because they make good decisions of the opponent. So we specify before a certain depth limit, let's say here 2, and every node which is closer to this, to the root, gets the model knowledge as soon as possible. So once we expand the search tree and the depth is smaller than d, it immediately gets the DCNN knowledge, and all other nodes which are below this don't get that knowledge. With the intuition that the closer we are to the root, the more important is the knowledge. And in the last scheme, first the principal variation. If you look at the tree, in every node we look what is the most played action. So here this one, here this one. So this is the principal variation. This is a variation which would be chosen by best play by both players. And then we just say, okay, if we are in the principal variation and then expanding nodes, they might be very important later for the outcome of what happens. So if we are in the principal variation, we also immediately use neural network knowledge. The problem is that the principal variation changes during the tree search a lot, and it's fuzzy, so it changes. Some are very, very close, then they change, and so on. So we specify some threshold epsilon. So we do not say, okay, we have to be in the principal variation, but close to. So we can, for example, say that here moves, which if here would be a move like played 900 times, we say, okay, we are still in the principal variation. And then we can use this threshold to determine how much of the search tree gets the knowledge. So these are the 4 schemes. And we did some experimental results. And I compared it to I call it upper bound. So the question is, what can an optimal scheme achieve? So an optimal scheme would be, we don't pay any execution time for the GPU. So we have a GPU which just gives us back the results without any time. So we made tournaments against Pashi, and we fixed the number of playouts per second, which is the easiest way to get exactly this result. So in 1 second, later we use 1 second per move for the tournaments. So in 1 second, Abacus roughly gets 11,000 playouts and Pashi 500,000 playouts. So we fixed these for the tournament. So Abacus was allowed to search for 11,000 simulations and Pashi for 20,000 moves. So you see that the bigger the networks are, the slower the average speed is. But in this, we have fixed the playout rate, so we still see that the win rate goes up and up and up. So this is also an example. The better your neural network, the better are your playing strengths. And you see that if you go from the basic version, which is basically also quite strong, so it's about 4 dan. It was 4 dan on KGS. So you would, in an optimal world, would increase the playing strength by about 700 EO. So this is optimal upper bound, which we later compare all schemes to see, okay, what do we lose by using replacement schemes? So I was just told I have not so much time, so I won't go into any details of the tables. So every scheme you find in the paper has such a table, where I first test synchronous and asynchronous variants for different parameters. For here is its expansion threshold, so 8 is the default, and we just increase to see how the win rate against Pashi changed. What I forgot to mention, as Abacus is much stronger than Pashi, we use handicap games of 7 stones, just to somehow bridge this large gap in the 700 ELOs. And yes, this is just the expansion threshold. What I found interesting is that the win rate doesn't get so much worse if you increase the expansion threshold. So if it goes here to 32, the search tree is much, much smaller, but I would expect a much lower win rate from here. So it's quite stable, which I found very surprising. And the asynchronous version with 16 was the best. and it has or had only minus 60 elo versus the upper bound. So by using this scheme, you only lose 60 elo points to the optimal. We did the same for the width threshold, which turned out to be the best scheme with 54, but very close to the expansion threshold. So we did not gain much, but it is very stable. If you even increase to 64, you don't lose much. So this is a very stable scheme if you don't have powerful hardware. Again, the asynchronous version was the best. Then we got the depth speed. This is maybe one fact which might be surprising is that here and here are high numbers. So basically there should be a 0. It shows when the knowledge is applied in a search node. So it means when we replace the fast predictor by the neural network, then there were already more than 2,000 playouts done through the node. This comes by the fact that we reuse the search tree. So we search for the first move, we get a 0 there because the search tree is clean. But later Hashi searches and then we search, we don't ponder, but we reuse what we have. And there we already have 2,000 playouts here, so it's quite an inefficient scheme if we reuse the search tree, which of course we do. Moreover, it was quite difficult to find good parameters for the depth. And so you see here that it's not as good as the other schemes. And most important, you have to tune it for the thinking time. So if you change the time for, let's say, 5 seconds per move, then you would have to redo all the experiments, which is so don't use the scheme. And this is the same for principal variation. Again, asynchronous variant got close to 71, and synchronous was worse than this. So let me summarize. The neural networks can improve playing strength in an optimal world by up to 700 elo, so they are very powerful. The only limiting factor is the execution speed. And if you don't want to put into, let's say, 8 GPUs into your machine, then you could use one of these 4 replacement schemes. The best parameters are in brackets, so the width threshold was best, closely followed by the expansion threshold. The asynchronous was always better than the synchronous one. So it really pays off to use the asynchronous version. And we compared it to an optimal one. And you lose only about 50 elo to this optimal. So instead of buying hardware, you could also just say, okay, I don't care about 50 elo if I can gain 500 elo and just use some speed. Future directions include, we only used policy networks here. And AlphaGo, during writing the paper, introduced these powerful value networks. And this question is what schemes are best for these value networks. And the big challenge there is that we do not have a good fast predictor. So one way might be to fiddle around with the selection formula. As we have the fast predictor, we have the playouts for the fast predictor. But it gets much more complicated than what we did here. So this is, yeah, I'm looking forward to how this can be done without using so many GPUs. That's all. Thanks for your attention.
Questions?
I had a little trouble understanding the difference between the visit and the expansion choices. Can you?
So the expand is just the usual Monte Carlo tree search.
Right.
You expand a node when you here have more than 8 visits, then you expand the node. Otherwise not.
And when you expand, all the nodes get
immediately the knowledge.
Oh, so every node will get the knowledge.
Or every.
So you're just sort of delaying. So you're keeping the tree smaller in some sense.
Yes.
Oh, I see. Okay.
And then in the width threshold, we don't keep the tree smaller. You just say, okay, the node has to be at least T executions to get the knowledge.
Right.
And some nodes just
So expansions on tiny nodes, then you don't worry about these
Yeah.
kind of things.
You just say, okay, they are not visited often.
Right.
Okay,
I see.
Okay, other questions? Yes.
Could you repeat where this optimal player or this upper bound comes from?
So, starting from the back, we do experiments with 1 second thinking time per player. So, we now said, okay, if we want to get rid of any dependence of the execution time, we just look at how many simulations you can do in 1 second, and then fix the number of players you are allowed to do during the tournament. That's how we came on these numbers. So they are equivalent to 1 second's thinking time. And if you know use the DCNN, then it doesn't matter if you, for example, this one would use about 5, the last one would use 5 seconds per move, but we just ignore it. Whereas
Yes?
Why don't you use CPU for, not GPU, but CPU for the inference? CPUs are not so slow.
first, GPUs are faster than CPUs, and second, the main point is,
For your case,
yes.
maybe I guess up to 8 times faster. Maybe 5 or 6.
Yes.
So using both GPU and CPUs help increase the performance.
Yeah, we basically do CPU, and because we first always use the baseline stuff, and then later that replaces by the GPU. So you could, for example, also use as a baseline a very small neural network which runs very good on the CPU, and then later replaced by a very big neural network which is run on the GPU.
So I hope in the future research how to control the hybrid mode, say using both GPU and CPU, and control use of CPU. I believe using both processors could improve.
Yes, of course.
Okay, maybe one short final question. So, are you using Grandmaster games to train? This is all online, right?
Of course, we use from expert. We use games
Okay.
to train in a supervised manner.
Okay. Well, that was a short question. Okay, thank you very much for this presentation.